So I think that was the last slide from last week, yeah. So yeah, we will have this afternoon classes because I was yesterday on Wednesday, on Tuesday I was at Poro for the recon trip for our field trip, yeah. So, and you can stay there in 2 villages. You will stay 3 nights in the one village at the west coast and 3 other nights in the village at the east coast. So, and then we will stay there for 6 days. So we will leave on Wednesday the 9th, I think it is Wednesday the 9th of September. We will leave here with the ferry to Poro. So when we will leave at 11 a.m. in the morning, that means you have then to be there at the harbor here in Suva. No, not at the harbor, at Suva. We are leaving from this other jetty, that is this jetty in Nausori. Yeah? Not Nausori, but it is on the other side. Yeah? There is a jetty. So when the bus will pick up us here, yeah? That is maybe 8 or 9 in the morning. Yeah? So and then this bus that is from Patterson will bring us to the ferry, and the ferry will then leave at 11 a.m. in the morning, and that means we are then at 4 p.m. in the afternoon we will be there in Poro. So in there you will be picked up from 2 trucks. You know they have no buses there because there are no roads, there are only footpaths. Yeah. So in there they have such trucks, yeah, and there you can then sit behind, and they will bring you then to this first village where you can stay, and I will stay at the resort. So and then I'm planning to do with you a 6-day trip. That means you are arriving on that Wednesday, then we have Tuesday, we have Friday, Saturday, on Sunday there is in this other village, you know, the church, yeah. So if somebody likes to go to the church, then you can go there in this village to the church. And on Sunday afternoon we will then continue with our field work. And then we have Monday, and then we have Tuesday. And on Tuesday evening the ferry leaves then sometimes during midnight. So and this ferry goes then from Poro directly to Suva. So and then you are back in Suva on Wednesday morning. So and everybody should wear good shoes, yeah, because these a lot of the passes are just foot passes, you know, maybe of this size, yeah. And the other streets, yeah, these are not the hard streets, these are all gravel roads, yeah. So you should wear good shoes, yeah, because we are always, or most of the time, we are walking along the beach, yeah, because there you can see all the outcrops. One can see there actually a whole magma chamber, yeah. You have there this orchite basalts, basalts with orchite inside. Then you have basalts with plagioclase inside. Then you have basalts with bows inside. Then you have some very coarse-grained basalts. They look like gabbros, yeah. So and then you have basalts which shows huge holes inside. That means there you had a lot of gas in the melt, yeah. So and then you have some lava flows, and then you have pillow lavas, and then you have these mantle xenolites. So and these mantle xenolites, these are these rocks which you can describe here with the MSH system. We have mantle xenolites containing forsterite and enstatite and spinel. You can identify them very easy because they are sitting as xenolites in these basalts, yeah. So and then if we have there actually enough time. I mean 6 days we can do them. There are then also some other things. I mean, it is also very interesting there from the vegetation. Yeah, there is nothing destroyed there. It is all original. And on the north coast, there one can watch the turtles, yeah, when they are coming out. Maybe you should also visit this place, yeah. So that's so far to the field trip. And Sue will come with us, yeah, because we are taking the departmental vehicle we will take with us. So then she can always carry the food and all this stuff, yeah. So that you actually have nothing to transport while we are walking around, yeah? Just something to drink. So, and your baggage you can then leave in the first village. So, and Sue will then transport all the baggage to the second village with the vehicle, because we are walking there. Yep. So, and hopefully this will not be raining, because otherwise it becomes then boring. So, but now let us just continue with this stuff. And this afternoon, I wrote you, we will have a class between 1 and 3, just to cover the things from last week, from yesterday. And the other thing is Neil is now sick. Yeah, he got something with the kidneys. So, and therefore I don't know if he can then make it next week for the practical. So, and if not, then I will just continue next week in the practical with the class, yeah. And when Neil becomes then healthy, then he can just use some hours from the lecture class for doing the practicals, yeah. Then we are not losing anything. So then let's just continue here. Here we have this field here, this dark blue field that is actually the field from our mantle rocks for this MSH system. So and there we have then the Harzburgite. So this Harzburgite contained for forsterite and enstatite. And if we have a rock containing only a forsterite, then we have a dunite, yeah? So and these dunites, Harzburgites and dersonites, this one you can find during our filtering, yeah? So if we are hydrating our Harzburgite, yeah, and I showed you last week that this hydration takes place only along fractures, cracks and so on in the oceanic crust, then you are forming from our forsterite and enstatite, you are forming then an antigorite, that is the serpentine, and this antigorite, I mean the high temperature antigorite, that is the high temperature serpentine, that is the antigorite. And if you are forming a serpentine at lower temperatures, then we have the chrysotile. So, and I showed you last week how you writing down these reactions. You are putting here your finger or your hand on the antigorite, and then you have the reaction. Forsterite plus water plus enstatite will give you the antigorite, and that is a so-called cross reaction, a triangle reaction, yeah? Because we have triangle reactions and we have cross reactions. And we will do this then also with you again in the practical. But for now, you should know we have here a triangle reaction. And we can have cross reactions. So, this one is the triangle reaction. So in the cross reaction, can we form a cross reaction somewhere here? No. Therefore, we need another example. So, and that is so for this MSH system, and we can subdivide this MSH system here into a binary system. Binary system is just this line between two end members. Here we have the periclase, here we have quartz, and here we have the ternary system between periclase, quartz, and border. So, but now we would like to make a lersolite, yeah? So, and the lersolite is also a mantle, is also a peridotite, but there is also CaO in the system, yeah? So, and therefore we need another triangle that we can make from our magnesium silica bearing rocks. also calcium-bearing rocks. So, and such a lersolite contains additionally a diopside, yeah? So in the diopside, you know by now that is also a pyroxene, but that is a clinopyroxene. And as the chemical formula, calcium, magnesium, Si2O6, yeah, that is then the diopside. So we have then an additionally component in our diagram or in our system that is calcium oxide. And then we are using this triangle, and that is the CMS composition diagram. And here between, on this binary line here between quartz and magnesium, we have again our mantle rocks, that is the forsterite. Here we have our serpentines. Here we have the enstatite and the talc. So, but now we are putting here water and CO2 in excess. Yeah, we can do this. And replacing here this comma, we are replacing water from our former diagram with calcium oxide. And therefore we can then form the diopside. So, and in this green field here, in the green shaded field, we have then the lersolites, yeah? So, and in the dark blue field here again, here we have the composition of our mantle rocks. So, and we can form in the same way reactions as before. For example, here we have an amphibole, and this amphibole is called tremolite. You know this from your manuscript. And there I have given you the formula from the tremolite, that is a Ca2Mg5 Si8 O22 OH2 mineral. Yeah? So, and if you are like to form now this tremolite, then you are putting the hand on your tremolite, and then it is diopside plus talc is tremolite. So, and now we can just check if this is true, because that is then important when we are starting to do our work or our practicals using the microscope, yeah? So, and then you can just use also your chemistries and your triangles, and then you can estimate what minerals are in your thin section, yeah? So, and now we are just trying to make a tremolite here. No, we are not making it here, we are making it here. The tremolite, and then we have here the diopside, and we have here plus talc. Yeah, here it is written talc. So, then you know the diopside, that is CamGSI2O6. And the talc, you know by now as well, is Mg3Si4O10 OH2. And then we are forming a tremolite. And the tremolite, if you are checking your manuscript, is Ca2Mg5 Si8 O22 OH2, and now we are checking. Then we need on this side 2 diopside, and we have 2 calcium, we have 5 magnesium, we have 8 silica, we have here 12 oxygen, 20 oxygen, yes, 22, and the OH2 group, and then your reaction is finished, yeah? So, and that is actually a very easy-going chemistry. And the same thing you can do also for all your other minerals which are written in the diagram. So now we can see the next thing. I mean, here, if we are putting CaO here, then we are putting in this comma calcite, yeah? So, and then we have a calcite has CO2. So, and then we have volatiles, and we have the volatiles, and this volatiles or volatile contains water and CO2. Therefore, we have clarified the next thing. The fluids in our mantle are mainly water and CO2. Yeah? I mean, there is also some methane inside, there's also some nitrogen inside, but mainly it is water and CO2. So, and that is because of the planetary water cycle. So, in the planetary water cycle, that is something very important, because without our planetary water cycle, no life would exist on Earth. So when this water goes down with the subduction, yeah? I think I showed this to you before as well, but it doesn't matter. I can just show it again because one cannot see often enough these diagrams. If we are just talking in the case of Fiji, yes, let us make a Fiji diagram. So here we have the highest elevation in Viti Levu, yeah? That is this mountain, and what's the name of the mountain? I don't know it, therefore I'm asking you. That is a mountain which is about 1,300 meters high. Mount Kasa. Is it? Or is it Mount Kafa? I don't know, but anyway, you saw this mountain last time when we went to the field. So and now it looks like this, and then here it looks like that. So and here we have some water. So and here we have also some water. Then we have here the oceanic crust, and that goes down here, yeah, because here we have the root of our mount here, whatever mount it is, that is the root here. Then we have here an oceanic crust. So, and then we have here our mantle slab, yeah. So, and that is the part where we have our gabbros and basalts here. So that is OC for oceanic crust. This here is also all OC in our case in Fiji, yeah, because it is mainly formed of oceanic crust, but I showed you during the EHES 106 field trip, you saw also the tonalite somewhere here, yeah? So, and that is then the differentiated oceanic crust. So, and then it is in Fiji the case that we have two subduction zones. I don't know if this is now true what I'm drawing here, yeah? So, because nobody knows it exactly, but I will figure it out during this time while I'm here. So, you have two subduction zones. One is dipping from the east, and the other one is dipping over here. It is dipping from the west, something like this. And here it is dipping from the east. So, and then you have here the other subduction zone. So, and we don't know if they are lying like this, or maybe by now they have flipped a little bit. I don't know. Therefore, one has to study all these rocks. Yeah. So maybe they are not that flat, because if they are that flat, then you cannot create this melt here, yeah? But these gabbros and these basalts were not formed from the dehydration of such a slab, because then you would have another chemical signature. But anyway, it looks like something like this. So, and in these parts you are getting then your mantle rocks. So, and yeah, that was the reason why I'm telling this, these volatiles which we have here, that is water and CO2. That is water and CO2. So, and this water this water goes down. This water goes down with the subducting slab. Yeah. So and the CO2 goes also down with the subducting slab, but there's also the production of CO2 from melt below or from melt in the asthenosphere. Yeah. So and this CO2, which will becomes also released at the Earth's surface, one can see this very good in Vanua level. For those of you who will do next semester the ES301, we will go there to Vanua level, and in Vanua level you have a lot of hot springs. You have all 45 hot springs. So and in these hot springs, this water is still boiling when it comes to the surface, and this water becomes heated up here from below somewhere. So and then you get Sabu Sabu. You know, in Sabu Sabu we will then visit the pearl farm. Yeah, pearls are only growing in a certain environment. Yeah, and these pearls are growing in an environment where you have certain components for the oysters, and you know these pearls are growing inside the oysters, and there you need CO2, you need methane, you need some nitrogen, and some other things in a very good relationship. Then these pearls can grow in the oysters. And in Sabu Sabu, if you are walking around in Sabu Sabu along the beach, then you can see that the water is everywhere swizzling. Yeah? It is swizzling like in the mineral water. Yeah? So, and that is the CO2 which becomes released from the Earth's mantle. And that is there everywhere the case, also at the ocean floor there. So now we are coming to another thing. We are coming going now again into the atomic structure, because we have certain modifications. We have our solid rock. If we are heating up our solid rock, then we are making from our solid rock melt. So in the most easiest phase diagram to describe all the modifications, that is water. So in water, that is H2O, as you can see here, and that is the structure of ice. Yes, if we are freezing water, then we are getting ice. So and if we are heating up water, then we are getting steam. So and these are the three modifications. So and water is also a mineral phase as every other mineral. But the other minerals, you have the solid phase, you are heating up, then you are getting a liquid, and you are getting the melt. So, and if you are checking water, or if you are checking by yourself the water while you are boiling it, at first you can put in your cooking pot some ice cubes, yeah. So, and then you are heating it up. Then at 0 degrees Celsius, this water will become molten. This ice will become molten. Then you are forming water, and at 100 degrees Celsius, you are forming steam. So. And when we are forming steam, then the volume of our water increases dramatically. Yeah? So, and that is also the case when you are dealing with minerals. If you are heating up the minerals, then the volume will extend. Yeah? So, and when the volume extends, that means the density will decrease. Yeah? So, and that is a very easy relationship, and you know this from school. That is rho is m divided by v, by the volume. So in rho, that is just the density, m is the mass, and v is the volume. So and if we are now heating up this ice, then the volume will increase dramatically. And that means the hydrogen bridges here becoming more loose. Yeah, they are just spreading in off. So, and here we have now a very easygoing phase diagram. That is the phase diagram of water. So, and if we are making phase diagrams, then we are using, most of the time, we are using the pressure and the pressure, I put the pressure always on the y-axis, and the temperature I put always on the x-axis, yeah? So, but there is actually no, there's no classification. You can also put the y-axis on the pressure on the x-axis and the temperature on the y-axis. It's up to you. So, but anyway, here we have the phase diagram of water, and here on this side, to very low pressure temperatures, we have solid, and that means we have here 0 degrees, somewhere here, yeah, that is 0 degree, and on this side we have ice, yeah. So if we are increasing the temperature, then we have here a mixture of liquid and melt. So, and if we have a diagram, or if we have a field where we have liquid and melt, that means we have water, and in this water are still swimming some ice cubes, yeah? So, and if we are waiting for a while, I mean it is also a time control thing, then more and more of the ice cubes are melting. More and more of these ice cubes are melting, and then we have just liquid. So now we are coming to this point, that is the boiling point. So and at the boiling point, that is then 100 degrees Celsius. Then we have here just steam, yeah? We have here then the transition between liquid and steam, and that at a constant pressure here, and this pressure here, that is then just atmospheric pressure, and that is 1 bar, yeah? So, and then we have here the critical point, and the critical point, there we have then an increase in the pressure, because if we are just going here and heating up, then we have a steam, yeah? We cannot, at atmospheric pressure, we are continuing just here, and if we have steam, then we have steam, yeah? There's no modification possible. But if this steam is under pressure, like in the Earth's mantle, then we are not, then we have not steam, then we have fluid. And this fluid is something like a plasma, yeah? So, and that we have here then at the critical point. And the critical point is at about 273 degrees Celsius. So, and there we will then make our fluid phase in the same way what I have written here. So that means, when I'm always talking about water in the Earth's mantle, there we have this fluid phase, yeah, because due to the high pressure conditions, yeah. So, and this fluid phase is very important, because without fluid in the Earth's mantle, no mineral reaction will take place, yeah. So, except our polymorph minerals, yeah. I showed you the polymorph minerals, and one very important or very common polymorph mineral, that is the mineral quartz, yeah. I showed you before this diagram, this pressure temperature diagram of the quartz, where we have the quartz modifications, yeah, and that was the alpha quartz, the beta quartz, and then to higher pressures we have then the coesite, and at very high pressures I cannot reach this field now. We have then the stishovite, and I gave you on the board here, exactly here I did it, this diagram where we have the stishovite inside the garnet, because if this mineral stishovite becomes then again lifted up to the Earth's surface, then it will go back into its, in this alpha quartz modification, and therefore the volume extends, and then you get these cracks in the stishovite. So, and now we have here another thing, we have here the triple point written, we have here a univariant line, and we have here a divariant field. So, and this divariant field and univariant lines and the triple point can be described by the phase rule. So in the phase rule, I will show you in one of the next classes when we are talking about more about phase diagrams and calculation of these curves. Then I will give you the phase rule, but for now, you should just know that the phase rule exists. So here another temperature pressure diagram, and that is just again in the ice system. Here we are going up from a temperature of 150 degree to 450 degree, but here we have temperature in Kelvin. So, and you know that at 25 degrees Celsius is 293 Kelvin. So a Kelvin, that is just the American system, and the rest of the world is using degrees Celsius. So, and here we have the pressure in Pascal. So therefore you have always to be carefully which units people are using, yeah? So you know by now that that 290 degree Kelvin is 25 degrees, is 25 degrees Celsius. So that means 273 degree Kelvin is 0 degrees Celsius. And if we have here, if we are going here, that is the 270 degree Kelvin, and here we have then 0 degrees Celsius, yeah? So, and here we have these modifications, pressure dependent modifications. We have here 1 Pascal, 2 Pascal, 3 Pascal, and if we have here 1 Pascal, 2 Pascal, 3 Pascal, then we have here in kilobars, 1 kilobar, 2 kilobars, 3 kilobars, yeah? So, and then here along this line, we have here the curve from solid to liquid. So that means here at very low pressures, close to atmospheric pressure, that is 1 bar here, yeah, multiplied by 10, then we or not by 10 multiplied by 1000, then we have here 1 kilobar. So, and here we have then our transition zone making from our ice water. That is then the conditions how it is in your kitchen. So, but if we are increasing the pressure, then we are then the transition between ice and water is at higher temperatures, yeah? So, and that is very important in mineral chemistry, because all our reactions taking place at a certain temperature and at a certain pressure. So, but and it is very temperature and pressure dependent. And even the melting point from water, from ice to water, is strongly dependent here on the pressure. So, for example, if we are going here to this 450 degree Kelvin minus 273, can just put somebody this in the calculator. 450 minus 273. Okay, that is then 177 degrees Celsius, yeah? So, and that means if we are sitting here and we have here 3 kilobars, and at 3 kilobars, the melting point from ice to water is here at about 170 degrees Celsius, yeah? So, and if they are then talking about ice on the Mars, yeah? I mean, there are a lot of new results from NASA that they found ice on Mars, yeah? And people are thinking that in the first 200 million years, there was water on Mars, yeah? So when you can, if you are using a huge telescope, or you are just downloading the picture from the internet, what NASA has made on Mars, then one can see sediments, yeah? So, and if you have layers of sediments, then you know there was weathering, yeah? So there was weathering in the first 200 million years of Mars after the formation of Earth and Mars and all the other planets. So, and there was then still weathering going on and deposition, and that shows that there must be some water have been on Mars. So, and they found now also a huge ice head on Mars, but on Mars it is much more colder than on Earth. So, and this ice is then maybe has a different crystallographic structure compared to those ice which we can find in our fridge for cooling down the Coke. Yeah? So here I have written 1, 2, 3, 4, 5, 6, 7 modifications, 8 modifications, and we are sitting always in the same chemical system, that means water, H2O, and if we have here 8 different modifications, that means then the crystallographic structure of our ice. Yeah? So, and all our minerals, when we are sending them down in such a subduction zone or in a continent-continent collision zone, or if we are sitting deep in the Earth's mantle, then our minerals are changing always the crystallographic structure. So in most minerals, they are changing the crystallographic structure and their mineral chemistry. Only those minerals, which we are calling polymorph minerals, they are changing only the crystallographic symmetry. So, and that is also a thing what I like to show you before the midterm break, roughly our different crystallographic symmetries, because after the midterm break we are starting then to do microscopical work. So, and the things what you can see, the features of every mineral under the microscope strongly depends on the crystallographic symmetry and on the mineral chemistry. So, and I would like to connect this part after the midterm break, because then the microscopic work is much more easier if you have this background. Yeah? So here another diagram, here again in Kelvin from 220 to 300, and here we have this curve. We have here ice, yeah, again here 0 degrees Celsius, something like this. Now here we have the ice, yeah, that is here, and then we have here the liquid, that is water, and along this curve, and that is such a rounded curve, we have then the transition zone from liquid to ice, and that is then a so-called dehydration curve, and these dehydration curves, when the water is going out of the system, they are always rounded, yeah? So, and I will show you later why they are rounded. So, whereas if you have solid-solid reactions, then they are always straight lines. So, and this depends then also strongly on the coordination of the polyhedra. So, and here we have 4 different bubbles, and these 4 different bubbles have different size, are of different size, yeah? So this could be a bigger bubble, could be a titanium, or no, not a titanium, that could be a calcium or a potassium or a sodium, and then we have a smaller bubble inside, and that is then, for example, titanium or silica. But we talked just now about the ice. It could be the bigger bubble, it could be the oxygen, and the smaller bubble, the hydrogen. So, and I showed you this before as well, or we talked about this before, that the crystallographic symmetry is strongly dependent on the size of our atoms, yeah? And here we have the radius here, and then we have here our atomic unit cell. So, and when I showed you all these diagrams about the octahedrons and the tetrahedrons, then one could clearly see, for example, in the system of the pyroxenes, yeah, if you have an autopyroxene, then the bubbles you have on the 2 m spaces, magnesium, and then on the tetrahedron side you have silica, and therefore you have you are sitting in an orthorhombic system. So, but if you are replacing one bubble with another bubble, then you are changing you can change the coordination of the polyhedra, or the whole thing becomes, or the whole thing is not longer aligned. Yes, that was just using the sodium and the chlorine. So, and that is salt, yeah? So that means here we have the sodium bubble, sodium, and here we have the chlorine. So, and from these things, that is then the sodium chloride system, and that is the halide, yeah? So, and the halide, that is the crystallographic structure of a halide, and the halide is salt, and the halide is cubic. So, and if we are talking about a cubic atom, then we have, these are the axes. That is the A-axis, the B-axis, and the C-axis, or if we are using this one, then we have the A-axis, the C-axis, and the B-axis. We are choosing always one atomic unit. So, and if we are sitting now in such a cubic system, that means A is B is C, so that is this. This axis has the same length as this axis and has the same length as this one, yeah? And the three axes are called A and B and C, and A is B is C. So, and here we have then the angles. We have this angle here, we have this angle here, and this angle here, and these angles are called alpha, beta, and gamma. And if you are sitting in a cubic system, then alpha is beta is gamma, that means the same angle, and it is then 90 degrees, yeah? So, and if we are changing, if we are putting some other bubbles inside, then it becomes disaligned, yeah? But we are doing this in the next few hours. I have there some movies, how this, how the crystallographic symmetry can be modified. So, and to describe then then our chemical formula like it is here, yeah, we are using then always one unit. So here, for example, again we have the quartz, yeah. So in the quartz, I showed you before, we have different quartz modifications. It is always SiO2, you know this by now, yeah? And if you are increasing the pressure or the temperature or both, then our quartz changes the crystallographic symmetry, yeah? So in the quartz, which we can find on the Earth's surface, that is a hexagonal quartz, that's the alpha quartz, and this one is an alpha quartz, because we are saying low quartz, and low quartz, that is an alpha quartz, and if we are lucky, then we can find here an alpha quartz. Maybe it is here. Yes, it is here, mineral 3. So, and here, if you are checking it, then you can see, just take this one and give it around, yeah. Just check this one and give it around. So, and then you can see that this alpha quartz, if you are looking through this way from the top, then you can see that it is hexagonal. Yeah? It has 6 corners. So, and that is the low quartz modification, and that means our tetrahedrons, and you know by now that the alpha quartz or the quartz is only formed of tetrahedrons, and the tetrahedrons are all connected to each other, yes, at every corner, and then you can see this hexagonal shape. So and now if you are heating up the alpha quartz, then you are heating up the alpha quartz, then you are making a cristobalite or something like this, then the connections, the bonds becoming more and more loose, yeah, and then your crystallographic system will change and the volume will increase for one atomic unit. So and if you are if we are heating up our alpha quartz, so if we are putting just more pressure on it, then the symmetry will also change. The symmetry will also change. I mean the crystallographic symmetry, but the volume will decrease, and therefore you are changing then also. The mass will be the same. The volume, the density will increase, and the volume will decrease. And here you have your hexagonal shape, what you can see from above. Yeah, that is everywhere here. That is everywhere a hexagon. So, and that is the tridymite, and the tridymite has not longer a hexagon here. So, in the tridymite, that is the result when we are heating up our quartz. Yeah? So, and that is a cristobalite, and the cristobalite is also a high temperature modification, and our hexagon is also gone. Yeah? You are forming then a trigonal mineral, or you are forming a tetragonal mineral, depending on the pressure and the temperature, what affects your quartz modification. So here we have the low quartz and the high quartz. So in the low quartz, our bonds are more loosened, and the low quartz modification, that is our hexagonal modification. So and here we have the high quartz, and the high quartz we are getting when we are increasing our temperature and pressure, and then our bonds become then more aligned, yeah, because the temperature is increasing. So and here we have just the different levels, yeah. I mean here these bubbles are of different colors, and that is just a different atomic level while you are going through a crystal, but I will show you this also later in one movie how this looks like. So and here we have now the phase diagram of the SiO2 polymorphs. Here we have the low quartz, yeah, with a density of 2.65. One cannot read it from behind, but you can then read it in your PDF, which I loaded up on Moodle. So, and here we have the different modifications, and one can see wonderfully how the density changes. Yeah, here the density becomes lower and lower because the volume of our quartz will increase while we are heating it up. Here we have the high quartz, and here we have the coesite, and if we are increasing the pressure, then we are increasing the, how is it called, then we are increasing the density as well. So, and here at very high pressures, in the stability field of the diamond, we have then a stishovite with a density of 4.35. I think this relationship is now clear, how the density changes with the pressure and the temperature. So, and that is for the water and for all other minerals as well the case. So now we have here again the forsterite structure, and I show it just again because one cannot see this stuff enough, because it is just to understand it then completely. The forsterite is an Mg2SiO4, and the forsterite is the inosilicates. Yes, I have told you this before. And these inosilicates, These are the olivines and the garnets, for example. Yeah? These are the two examples which I gave you for the inosilicates. So in these inosilicates, you have then always isolated tetrahedrons. Yeah? So and here we have your tetrahedron, then we have here the oxygens. So and this oxygen is colored in light blue, whereas these oxygens are colored in dark blue, and that depends if the oxygen is sitting on the top of the tetrahedron or at the bottom. Yeah. So and here the oxygen is sitting on the top, and these ones are sitting on the bottom. So I have written here oxygen at a quarter A and 3/4 A. So and then we have the same for the magnesium. The magnesium are the smaller bubbles, here the red one, here the green one, and that depends on which level this magnesium is sitting. So and here one can see again the olivine structure parallel to the 1, 0, 0. The 1, 0, 0 axis, that is this axis, because you are making them always in a room. So then we have here 1, 0, 0, that is 0, 0, 1. And that is 0, 1, 0. We will do this then also more in detail when I'm showing you these movies. So, and then we have here an ideal hexagonal closest packing model. These are the M spaces. You know this by now. These are always the octahedrons. So, and the T spaces are the tetrahedrons. So, and here we have the actual structure. That is how it looks like in nature. And then you can see the arrangements of our octahedrons and the tetrahedrons varies a little bit. So and here this is the tetrahedron, yeah. There is the silica, there is the silica, and here on the M spaces we have our octahedrons, and we have two M spaces. One M space can accommodate bigger atoms, and the other M space, the M1, can then accommodate smaller metals or atoms, yeah? So, and that changes then always with, in natural crystal, that changes then always this arrangement dependent on the pressure and the temperature. And here we have C and B. So, and you know by now that here is the C axis, that is the B axis, and that is the A axis. So here we have another model of a Forsterite, and this just shows you, here we have the tetrahedrons where our silica is, and these tetrahedrons are always isolated if we are talking about olivines or garnets, and here the bubbles, that is the magnesium. And here we have always this overlying form of tetrahedrons, and that is just the case we are going then in 3D. Yeah? This tetrahedron is just behind this one. Yeah? So, and here we have another Forsterite structure where the tetrahedrons and here the magnesium bubbles, which are the octahedrons, they are just arranged in another way. And why they are arranged in another way, we have other temperature and pressure conditions for this second Forsterite structure. So, and what you should have in mind for your class, that you are always changing, or you can change your atomic arrangement, but while you are increasing or decreasing or changing the pressure and temperature conditions, yes. So, and therefore, when you are changing this, then you are changing the density and that is always dependent where you are sitting in the Earth's mantle. So, and now see you again at 1 o'clock.